Welcome to the second of our two-part installment on second-order sensors. In this lesson, we'll take a look at the response of second-order sensors to sinusoidal inputs. For a sinusoidal input, our forcing function is now going to be a sinusoid. And in this case, that sinusoid has a frequency of omega and an amplitude of A. As a result, then, I can write the governing second-order differential equation like the following. And you'll notice here I have my coefficients, 1 over omega n squared, and the other coefficient, 2 times zeta over omega n. And I also have my static sensitivity, k, times f of t, which is a times sine of omega t. And once again, our time response, y of t, will have two components, a transient component as well as a steady state component. And as we see here, the steady state component of our time response, that's going to have a different magnitude and a different phase that are dependent on the input frequency. So if we look at the steady state component here, what we find is a dependence on the magnitude, and we could write that as effectively a 1 over square root of this quantity, as well as a phase dependence, a phi of omega. And in this case, for a second order system, that'll be minus the inverse tangent minus the arctan of this quantity here. And so you notice then, for the second order sinusoidal response, both the magnitude and phase are dependent on the damping ratio zeta, the natural frequency of the system, as well as the input frequency, so omega n as well as omega. Let's rewrite this equation then as the following. Y of t will be equal to the transient component of my time response, plus k times a, where k is that static sensitivity and a is the amplitude of my forcing function, the amplitude of my input, f of t, multiplied by the magnitude ratio of my system, m of omega, all times sine of omega t plus phi, so sine of omega t plus the phase component of my response. So similar to a first order system, I can plot a Bode plot, a plot of magnitude ratio and phase for my second order system. So let's start with the magnitude ratio. Here we'll also have three cases, just as we did for the first order system. Let's start then with the case where omega divided by omega n is much less than 1. And I could rewrite this as omega, my input frequency, is significantly less than omega n, the natural frequency of my system, or in this case, of my sensor. In this case, this term here, this omega divided by omega n squared, you basically have a small number over a large number. So this term is effectively 0, as is this term here. So you're left with 1 over the square root of 1, or 1. So my magnitude ratio, capital M of omega, is equal to 1, which is equal to 0 decibels, 0 dB. So at very low input frequencies, my magnitude ratio is equal to 1. My second case occurs when omega divided by omega n is equal to 1, or in other words, omega, my input frequency, is equal to omega n. It's equal to the natural frequency of my system. In this case, these omega over omega n terms, they equal 1. Right? So this term drops out. 1 minus 1 is 0. And I'm left with 2 times zeta squared, but then I take the square root of that. So in the case where my input frequency is equal to the natural frequency of my system, my magnitude ratio is equal to 1 over 2 times zeta. Or equivalently, I could write that as minus 20 times the log of 2 zeta in terms of decibels. And our final case then will be where omega, the input frequency, is much larger than the natural frequency of my system. So I could write that as omega over omega n is much larger than 1, or equivalently, omega is much greater, much larger than omega n. In this case, this omega over omega n squared term here is then squared again, so we end up with an omega over omega n to the 4th power. And what happens is that ends up dominating the magnitude ratio. Even though there's a squared omega over omega n here, and of course a 1, for these large input frequencies, the magnitude ratio ends up being dominated by this omega over omega n to the 4th term. So if we take the square root of that, we end up with 1 over the quantity omega over omega n squared, or equivalently omega n over omega squared. And in decibels then, this will be minus 40 times log base 10 of omega over omega n. So let's plot this magnitude ratio response. According to my three cases, if I look at the first case, for low input frequencies, for low values of omega, I should have a magnitude ratio of 1, so my output should be equal to my input. And if you look at low frequencies input to my sensor here, you'll see on the magnitude ratio portion of my bode plot that the magnitude ratio is equal to 0 dBs, right, or is equal to 1. If I look at high frequencies then, so if I look at large input frequency, large values of omega, what I'll find is that in the case where omega is equal to 10 times the natural frequency, my magnitude ratio will be minus 40 times the log of 10 omega n over omega n. So that'll be log base 10 of 10. So as a result, I'll have a magnitude ratio equal to minus 40 decibels, minus 40 dB. If I increase that input frequency to omega equals 100 times omega n, I'll find a magnitude ratio equal to minus 80 dB. So if I come up to my plot here and I look at a input frequency of 10 times my natural frequency, and I've set this system up, this arbitrary system here, to have a natural frequency of 1 radian per second. So at an input frequency 10 times that, you'll notice I'm at a magnitude ratio of minus 40 dB. And if I were to follow this line down here, for an input of 100 times my natural frequency, I'd actually end up at minus 80 decibels over here. So what that's telling me is for large input frequencies, my magnitude ratio tracks down at a slope of minus 40 dBs per decade, right? So an order of magnitude is 1 decade in terms of an input frequency. And for large input frequencies, much greater than the natural frequency of the sensor, that magnitude ratio tracks down at a slope of minus 40 dBs per decade. If I look at the second case then, the case where omega over omega n is equal to 1, or equivalently, my input frequency is equal to the natural frequency of my system. What we found was that the magnitude ratio was equal to 1 over 2 times zeta, or in decibels, that was minus 20 times log base 10 of 2 times zeta. So now at this particular input frequency, there's a zeta dependence on my magnitude ratio. So what I find is for small values of zeta, I actually get a bit of a bump occurring here. So for this system, I've set it up with a zeta of 0.2, and you'll find for the low input frequencies, I'm at a magnitude ratio of 0 dB. I sort of track up to this bump associated with a zeta of 0.2, and then make my way down to the minus 40 dBs per decade slope associated with the higher input frequencies. So again, there's this dependence. In the case where omega is equal to omega n, there's this dependence on zeta, on the damping ratio. So what I've shown here is for a damping ratio of 0.2, if I decrease that damping ratio down to a zeta of 0.05, I'll find that this bump rises up to 20 dBs. So for smaller values of zeta, I get an increase in this bump. And as I increase my value of zeta, I'll smooth that bump out effectively. So here is a zeta of 0.5, and you'll notice I sort of track from this 0 dB low frequency magnitude ratio and sort of gently curve into this minus 40 dBs per decade slope associated with the higher frequencies. So you'll find these larger peaks here associated with systems that are effectively in resonance, right? So as my zeta value is decreasing, I'm losing any damping, and of course as that goes to 0, that would be an undamped system. And as the damping goes down, I get a bit of resonance here about omega n, the natural frequency of my system. So it's important to recall then the magnitude ratio and the plots associated with the first order sensors, now in contrast to the second order sensors. For the first order sensor, you'll recall that slope was minus 20 dBs per decade, where for a second order sensor, we're looking at minus 40 dBs per decade. And for first order sensors, we were never able to get a magnitude ratio greater than 1. Effectively, it was impossible. But with the second order sensor now, for systems that are in resonance or for low damping ratios, we can actually get a system that will produce a magnitude ratio greater than 1. So that's something different, something unique about second order systems when contrasting them to their first order counterparts. We can also take a look at the phase response of these second order sensors in a similar fashion. For the case where omega over omega n is much less than 1, or the input frequency is significantly less than my natural frequency, this will end up being a very small number, so my phase will be equal to 0 degrees. In the second case, where omega over omega n is equal to 1, or my input frequency is equal to the natural frequency of my system, what I'll find is I'll have a omega over omega n. This term will be going to 1, so I'll have 1 minus 1, or 0 in the denominator. And if I take the inverse tangent of that, if I take the negative arctangent of that, I'll find that my phase is equal to minus 90 degrees. And finally then, when I have omega over omega n is much greater than 1, or my input frequency is large relative to the natural frequency of my system, I'll find that my phase is equal to minus 180 degrees. And so if I plot this on my Bode plot, what I'll find is in terms of input frequency, this is logarithmic again, and then phase I've plotted here in degrees. For low frequency inputs, I have a phase of 0 degrees. For high frequency inputs, I have a phase of minus 180. And in the case where my input frequency is equal to the natural frequency of my system, as we see here, I have a phase of minus 90 degrees. So for low input frequencies, I have 0 degrees. That tracks down to minus 90 degrees of phase, and then tracks down to minus 180 degrees of phase for large input frequencies. So as was the case for the magnitude ratio, our phase plots, our phase also has a dependence on zeta. So the sharpness, the steepness of my transition from these low frequencies down to my high frequencies has another dependence on zeta. For small damping ratios, we find this transition to be steep, and for large damping ratios, systems that have a larger amount of damping, we find this transition to be more gradual, from these low input frequencies gradually then up to these larger input frequencies. But for all cases, they all transition through minus 90 degrees of phase in the case where my input frequency is equal to the natural frequency of my system, omega n. Once again, contrasting our first order sensors with our second order sensors, if you recall, for the first order sensors, we leveled off at minus 90 degrees of phase. So for low input frequencies, we had a phase of 0 degrees, and that transitioned down to minus 90 degrees of phase for higher input frequencies. For our second order sensors, however, we're at 0 degrees of phase for our low input frequencies, and now we transition down to minus 180 degrees of phase at the higher input frequencies. So the second order sensors, they add an additional minus 90 degrees of phase. And then at the natural frequency of the system here, we're at minus 90 degrees of phase, where equivalently for the first order sensor, we were at minus 45 degrees of phase at the time constant of the system, when omega times tau was equal to 1. And finally, let's take a step back and take a look at the big picture. If I have a sensor and I have some measurand that I'm trying to measure, maybe it's, in this case, a pressure, and this pressure has some oscillatory nature to it, right? So it has some sinusoidal behavior that's input to my sensor. And let's say the sensor has a particular sensitivity defined as volts per Pascal. So it takes some pressure input and gives the user some voltage output. So the other thing the sensor might be doing is giving me some phase and amplitude shifted version of the measurand that I'm actually trying to measure, right? So based on the Bode plot of this sensor, I could describe this output sinusoid given the input sinusoid. Now, I'll have the same frequency, so I'll have the same period for both my input signal and my output signal. But the attenuation due to the magnitude ratio, as well as the phase, they can give me some significant impacts on my measurements, right? I can have a delay associated with the phase, and based on how my system is set up, this attenuation can be significant and have a significant impact as well. So the big picture here is that we must pay attention to the frequency content of any of the signals that we're trying to measure, as well as the performance and the parameters of the sensor that we're using to attempt to measure those signals, right? For a first order sensor, we need to really have a good understanding of the time constant of that sensor. And for the second order sensors, we need to understand and appreciate both the damping ratio and the natural frequency of these sensors. And the point here is that the output, the information that we're storing with our system, we need to be able to describe the performance of the sensor such that we can, accurately say the measurand is performing this function or behaving this way, and that the behavior we're seeing, the behavior that we're ultimately storing in terms of data acquisition, is not due to the sensor itself, right? It's actually due to the measurand, the thing we're trying to measure.